I'm Dr. Usha Rani, Professor EEE Department, RMD Engineering College. I'm going to brief about the two area load frequency control tie line power. Uh, in general, if you take care of the objective of two area LFCs, first one is to regulate the frequency of each area. Second one is to simultaneously regulate the tie line power. Both you should take care. One is regulate the frequency of each area, another one to regulate the tie line power. So in the case of frequency, if you consider, if you include a proportional plus integral controller, okay, the steady state error gets 0. In the case of interconnected power system, the derivation proof shows that the steady state frequency error is reduced by 50%, as well as the tie line power line is also reduced by 50%. So we are going to take care of one example problem. Here first I have taken the question as a two area power system connected by a tie line. As the following parameters, they have given area 1, area 2, the turbine output power in megawatts 4000, 2000, nominal frequency 50 Hz, both areas, speed regulation 4% and 5%, power system gain 50 and 125, governor time constant 0.2, 0.1, turbine time constant 0.3, 0.25. They have given a load change of 80 megawatts occurs in area 1. That time, determine the steady state frequency and change in tie line power flow. For that, first I have calculated the beta 1. Beta has area frequency response coefficient or characteristics of area 1. Beta 2 has area frequency response coefficient of area 2. The formula has beta general formula has B plus 1 by R. B has load damping constant, R as speed regulation. So the unit here is per unit megawatt per hertz. So you are bringing the calculation in terms of per unit megawatt per hertz. So for that, first I have calculated B1 for area 1, 1 by the power system gain they have given. So I have taken 1 by 50, which is 0.02. Similarly, area 2 I have calculated B2 damping coefficient, that is 1 by kps2, 1 by 125, which is 0.008. And R1 I have calculated 4% is given for area 1. I have taken that unit as hertz per unit megawatt. For that I have multiplied that by FR1 by PR1 into PR1. So if I do that simplification, my answer is 2 hertz per unit megawatt. Similarly, for R2, I have calculated for 5%. If I calculate that, my answer is 2.5 hertz per unit. So with the help of these values of B1, R1, beta 1 is calculated, which is B1 plus 1 by R1. I have substituted that values 0.02 plus 1 by 2, which is the value of 0.52. Similarly, for area 2, the beta 2 value is B2 plus 1 by R2, B2 was 0.008 plus 1 by 2.5, the answer is 0.408. So the coefficient that is A12 as PR1 by PR2, the base power they have given us 4000 for area 1 and 2000 for area 2, so which is the answer 2. And delta PD1 load change in area 1 as 80 megawatt, so 80 divided by PR1, that is PR1 value is 4000. If I substitute 0.02 as the answer. In the load change in area 2, they didn't mention in the question, so we have taken as 0. So the formula for delta F static as, which is equal to minus of within bracket delta PD2 plus A12 into delta PD1 divided by beta 2 plus A12 into beta 1. In that I have substituted all the values. After simplification, my answer is minus 0.0276 Hertz. That is the delta F static frequency. Similarly, delta P tie line static I have calculated using the formula of beta 1 delta PD2 minus beta 2 delta PD1 divided by beta 2 plus A1 to beta 1. I have substituted all the values. After simplification, I have multiplied that by the PR1 because I need the answer uh, in megawatts. So I have substituted PR1. There is a load change in only area 1. So we are multiplying that by PR1. The answer here is minus 22.54 megawatt. So the tie line power as well as the steady state frequency gets interconnected power system. It has reduced by 50%. The main objective of tie line load frequency controllers. First objective to regulate the frequency. Second one simultaneously the tie line power. So you have seen the example sum. Thank you.